Welcome to Build with Naz. My name is Naz. I'm the founder of Rebel and the maintainer of the Rebel Open Core repo, which is a repo where we publish a whole bunch of really cool text user interface related crates. So in today's live coding video, I wanted to go over the need for box and pin. So in a lot of previous videos where I've covered asynchronous code, like things like cancel safety in Tokyo, or asynchronous code in general, because the way Rust features work and essentially asynchronous functions get expanded into a future, which is a struct, and it's essentially a state machine where like an executor, like a Tokyo executor, can essentially run the code up to a certain point, and then as soon as it hits an await and the future is not ready, then it gets essentially the executor goes and does something else until the waker is called, and then it gets to be pulled again. So essentially these futures are stateful and they don't do any work until you pull them, and the executor won't pull them until there's a .await call at the end of the future. So there's other videos on async. I don't want to get into that too much, but that was just kind of like a background for why I thought to make this video, because I was like, well, why is there a need for both box and pin? Because there's situations with asynchronous code, especially for cancel safety and in some scenarios where you need to not only have a box so that you can allocate some memory on the heap so that it's stable, but then you also have to pin the reference to a pointer to that memory so it doesn't move around between calls. Basically this whole thing I described with the executor going in and essentially polling a future and jumping in and jumping out of the state machine. In between the jumping in and jumping out and jumping in again, the references, basically memory addresses, can't have changed. So, and the way Rust ownership works, when you move something, it actually moves it in memory. So in order to understand why we need box and pin in these situations, I decided to create a bunch of tests in this particular video that we're going to be going over, where we can deep dive why you need both. And so before I actually start, let me do this. Let's create a new project first. And oh, what the, oops, it's code. And then let's see. All right, so here we have, okay, what is, oh, oops. Okay, so first, actually, let's do this. We also need a cargo toml. And actually, if this is what we want in here, oops. Here we go. All right, so we need, these are just some dependencies that we're going to be using when going over this, when creating the test. Serial just runs tests in Rust by default. When you run a test, it runs in parallel, so this makes it so that they run in serial. And cross term we're going to be using to colorize our output to make sense of a lot of the console log, or the, sorry, println statements that we're going to be generating to make sense of all of this. So let's clear this out. And so the first thing I want to get started with before I write my first example is let's do a quick background into heap and stack, because this is going to be information that we'll need to have at hand in order to understand this whole live coding session. So I have a link to this in the repo. I'll make an article out of this video, and this link will be in there. But please do take, if you're not familiar with this, please take some time and review this. This is fantastic. So essentially, when you write some Rust code, you compile it, it turns into a binary. That binary gets loaded to memory, and when that binary runs, the operating system calls that program a process. And so you can run a program any number of times, and each time you run it, they can be run in parallel. Each essentially running program is called a process, and the process has a whole bunch of memory that the operating system manages for that particular process. And this goes into how roughly that works. We have this thing called a stack and a heap, and there's a whole bunch of binary data goes the whole binary for your program gets loaded into memory as well. So when you have like string slices in Rust and they have a static lifetime, that's because those string slices are actually baked into the binary of the program. So there's a valid address that Rust can use to get the slice, and that's roughly down here. So, but we do have this notion of addresses. So, and if you have like I have a 64-bit machine, so my addresses are 8 bytes wide. So it's 64 bits. So I don't want to belabor this because this might be pretty obvious to a lot of people. But so the main the main two ways in which memory gets allocated in a program, like let's say when your main function is running, one is the stack. So the stack is like this is the notion of size is associated very closely with stack. So if the compiler knows how big your data structure is, then it can allocate it on the stack. And if it's allocated on the stack, generally speaking, it's faster than going to the heap, which is a different place in memory. And there's a variety of reasons for this, but essentially there's latencies and things. Like memory access isn't free because if you consider the CPU and the RAM, the CPU actually lives in a particular place on your motherboard, and there's a whole bunch of wires that connect it to the RAM, and then there's things called caches on the CPU and all kinds of stuff. So it gets pretty complicated why some of these memory accesses are faster or slower, but generally speaking, when you have something which is on the stack, it's easier to get to, whereas if you have something on the heap, which we'll discuss in just a minute, it's a bit slower. There's a dereference that's to happen on a pointer. So in this example, when you say int a, it actually it knows the size of a. Let's say it's a U8 or whatever. I mean, this is C++, but let's just say this is U8 in Rust. So it just allocates, it says that, okay, A itself is a place on the stack. So this A is a label, and that has an address. And what's inside of that address is, if you say A equals 0, then the thing inside of it would be 0. So it would have an address, and it would have a value. So that's the stack. There's no dereferencing. It's just what you see is what you get. So then you allocate another variable like b, you set it to be -3, now it's pushed down the stack, it has a different address, so b is just human readable for us, but for the compiler this gets turned into an address. And the way computers work is you always have this notion of address and value. So all the instructions in assembly for x86 and most other ISAs or instruction set architectures are kind of made this way. So essentially now, okay, so we have A, B, they're both allocated on the stack. So the compiler knows what the size is. A and B are for human readability, so these are actually memory addresses. So in Rust, if you were to assign B to A, a move would happen. And it's actually an actual move. It's not like just a metaphorical move, but the address changes. And we'll see that in some of the code that we're writing. And that's part of the ownership model. So if you don't want it to move, you borrow it. And then you can't have, you can have many read-only borrows, but if you want a write borrow or a mutable borrow, then you can only have one mutable borrow in scope. Like you can't have multiple. And that's where you have these ownership rules and so on. It's a really fancy way of doing memory management so that you don't like leak memory or do bad things. So so here again we're allocating another known, because it's an int. There's a value of it. So where it gets interesting is these pointer types, and again, this is C++ code, so just kind of like squint at it a little bit. For Rust, we have references, like there is such a thing called ampersand and so on, but essentially a pointer is a place in memory, and what it holds inside of is another address. So it's a way to dereference. So it's like it's indirection. So in order to get to the thing, you have to dereference it. So the thing is somewhere else. You take the address of the thing, you put it in let's say here in the stack, and if you want to get to the thing, the value of the variable in the stack isn't what you want. You want to dereference it, and then you want to get to the thing that is pointing to. So that's roughly the game that we're going to be playing in this example, or in this video. And so this is C though, not Rust. And then, so here, let's say we call a function called hello. Hello gets its own stack. Is out, like, let's say tail-end recursion works. It basically relies on the fact that this kind of mechanism is happening and the operating system automatically provides a stack for functions that are being called. That's why you don't have to explicitly allocate a stack. Or you could and get rid of tail-end recursion. But so here we have another function called hello. We call that, and it's returning a bunch of stuff. And it basically returns 100. So this is roughly how the call stack works when 100 comes back. So this is why it's when a function exits, it dumps all of its stack contents, and if it returns something, then that can be essentially remembered by main and then stored somewhere. So in this case, like D is now 100. So there you go, and then main returns 0. So this is roughly what's going on inside of the stack. So what is this heap? So let's say you don't know the size of something, because it's growable, like a vector. An array you can stuff on the stack because you know how big each item of the array is, and you also know how many items there are in the array. But if it's a vector, then that's not possible. Also, if you have like a bunch of trade pointers, so you want to use the din keyword in Rust, then it gets interesting because the size of the thing that the whole point of din is that we don't know what the size is. And so we're doing type erasure. We're saying that, okay, there's a struct which has a known size, but I am going to ignore that fact and I'm going to access it as if it only implements a certain trait, and that's a trait pointer. So trait pointers, like, what size is it? Well, you have to then you have to usually box it so that the box itself has a size. So, and I'm getting ahead of myself, but we're going to get into this in just a minute. So yeah, it gets a little bit more complicated with dereferencing and indirection. So but those are some of the use cases why we would actually need to have this, like, allocate things on the stack, on the heap, and why box is so important. You'll see this when you return a result, like sometimes it'll say box din error, and that's roughly why that's happening. Okay, so let's look at the heap before we get into the box. So in this example, let's go back. Yeah, okay. So here, let's say that we allocate something on the heap. So what happens is that on the stack, we end up with a pointer. So the pointer is just a variable which has a value. That value happens to be not 0 here, but it's actually a memory address for some place on the heap. And that place on the heap with that memory address actually contains the value 0. So 0 is no longer in here. We have to follow this blue line to get to some other place in memory, and then from that other place in memory, we can then get the value. So you'll see like star and then some variable. That's a way to dereference a pointer to get to its value. So what it's essentially a pointer and a pointee. So the pointee is the thing in the heap, and the pointer is the thing in the stack. And the pointer, it's sized because the pointer is a memory address, which, like, usize on my machine is 64 bits, 8 bytes. It's a known size. But what it's pointing to, the pointee, can be whatever size. And that's the whole point of boxing something. So a box in Rust. So this you can go through this example. Even though this is in C, it's relevant where multiple things can point to the same thing on the heap, which can happen. See, C1 and C2, even though the memory addresses on the stack for, the variable C1 and the variable C2, their memory addresses will be different, but their what's in the stack for their memory addresses will be same address as this thing on the heap, and we'll see that in the example actually. So it gets pretty complicated. Like, this is not in Rust. The whole ownership thing is one of the reasons for borrowing and ownership and such is so that you don't have to do pointer arithmetic and don't have to do all the things that I'm showing you right now. So this is kind of like what you might have to do if you wrote unsafe code, if you wrote code like with that calls into C code through FFI, stuff like that. But it does help to understand box and pin. So there you go. Please do check this out. This is a fantastic resource, just as a general knowledge for like what the heck is going on with heaps and stacks. So with that, but that's C++, so or C. Let's just come back to Rust. So in Rust, there is a way to get to the address of a variable, and you can do that one of two ways. So you can actually call a std pointer address off. So let me show you this. This is, what is this, address off? So you can do this one, std pointer address off. So you basically, and it's a macro because it doesn't know what your type is. So that's why there's a macro here. Makes sense. So basically, you give it an expression, and it'll be like, okay, I'm gonna go get the address of this expression. And so another way to getting it is just put an ampersand before the variable, and then you can tell format or println to basically print it as a pointer. Oops, not uppercase. Print it as a pointer. There we go. So that's another way. So we're gonna explore both options here in just a minute. So this is a lot of background information before we even begin with the examples. But without this background information, if let's say someone is not aware of that, the examples won't make any sense at all. So okay, so in Rust we have these things called smart pointers. We saw like not so smart pointers here. These are C pointers, C++ pointers. So in Rust we have smart pointers. So what the heck is a smart pointer? So a smart pointer is like a pointer. Like it's a thing that holds a memory address for something else on the heap. They provide not just the address, but also additional metadata and capabilities. So they do things like reference counting in some cases, ownership management, and they can also deallocate things when they've gone out of scope. So things like the actual drop implementation. So like you just create a struct, and then as soon as it goes out of scope, Rust will drop it. If it's on the heap through a box, it'll drop it as well. And so all of that information, all of that stuff, capabilities we get thanks to smart pointers in Rust. So box is a smart pointer, and it essentially allows you to lift a value that's on the stack and put it on the heap. So that's the simplest way to sort of describe what it is. So before we get started, let us write some ways to print memory addresses, because this would be like, let's just visualize. See serial. Let's just do this. We'll say print address. Print pointer address size. Okay. So let's say that we have a variable, and it's a U8, and the value is 100. So oops, I need to import this. There we go. All right. Actually, let's do all our imports because it's annoying. Let's do these. There's another import that we'll need in just a minute. Okay. So let's say that we have this variable x, and we want to print its address. Like, how do we get its address? So one way is using this this approach, the macro address off. So let's do that. So we say x address. We can do something like standard pointer address off, and then x, not a reference to x, but just straight up x. And then we can say println. Let's see, this is the value of x, and this is the address of x. So let's see what we get when we run this. Okay. So actually, let's do this. Instead of, we can actually do this. So because we can say cargo run, oops, cargo test, no capture, actually show output, and we want whatever, print. So this is I'm just running this test in the terminal. Okay, so that way I don't have to keep closing these windows that VS Code pops up. So here we have, let's clear the output. Okay, so we have X, the value of X is 100. And look at this address. It's a memory address, and it's a memory address of this thing on the stack. Pretty cool, right? So we got the actual address in memory. So this isn't the actual physical address in memory, because operating systems do this thing. They're called the virtual memory and stuff like that. But it's that number gets eventually translated to an actual place in RAM on my System 76 computer right now. So so that's kind of like one way to get the address. Now what we could do is just for formatting reasons. The reason I have this cross term pulled in is because I like to format the output so that it's prettier or easier to understand. So let's say that this is kind of made up because it's pretty easy. Actually, we don't even need these. We can just do like this. So let's say I wanted to print this one in a different color. I could just say blue. And what is X? Oh yeah, I can't do that. So we can say format like this, and then we can do like that. So basically that'll bring in why is this not? Oh, right. So X, and then this one we can turn into blue, because what this is saying is that I guess we could have just done this. We can just say X to string, turn into a string, and then colorize it blue, and then that gets filled in here. And then here we can, this one is a U8 also, so we can say to, so this one we should do this format. So we're going to format it into a string and then make it red, something like that. And it's, there we go. And that's a debug formatter. So now when we run this thing, it should look nicer. There you go. So there it is. It's blue, and that's red. So then you can do other things like underlined, and you can do like italic and bold and all kinds of stuff. So it's pretty fancy. You can even set background colors. So that's one way. This is using to get a memory address of a variable. Let's try a different approach. Remember I said there was another way, which is just to use the formatter, the pointer formatter. So pointer to what though? So let's say we have X. So that's our variable. Let's get a pointer to it. So pointer to X would be like that. And then we can then get the address of it. We can say X address 2, and here we can say format like that. So essentially we're saying that, okay, grab the, in fact, why don't we just simplify it and just do this. There we go. So now we have an immutable reference to this thing on the stack. And actually this what is this, ampersand X, yeah, and we're basically saying, okay, what's the address of it? I want to get the address of this thing, and but I want to take a different approach. I don't want to use this macro. I just want to use the formatter with the :p specifier. So let's dump that and then see what happens. We're going to call this xadder2, and let's say it should be the same. So blue, red. Let's do. Let's not do italic on that one. Okay. Actually, let's do italic on both, and this one I'm going to do on black. So this gives it like a different background color. So let's run it and see what happens. So look at that. They're the same. If I wanted to make the sort of spacing the same, I could do like that. And here you can see the value of X is the same either ways, and then and the address of it on the stack is the same whether I come at it from this macro or I just use the formatter with :p on a reference. So to kind of generalize this, because we're going to be using this over and over again, I have made some macros that we can use and I won't go into the making this. It's just basically string formatting. So this is basically the we can use this print. This takes an expression and it says, okay, what is your address, and also what is your size. This does something similar, but this is for a pinned reference or a pinned variable. So we'll talk about this later. And this is just a convenience, just so we can compare three things. So let's come back to our test. So this is the sort of the simple way that we did it. Let's try a different approach. So let's do using, okay, now we're going to do the macro using, that's exactly right. So here we say xadder3 is whatever this macro is, print pointer address, and what it does is it gets the address of the %x, and then it also gets its size in memory. So since it's a U8, it should be, so here's the thing. The reason I made it U8 is because the size of a U8 is 1 byte, but the size of these pointers is 8 bytes. So that's an easy way to see whether you're dealing with, in this case, a value or a pointer. And you'll see what that means in just a minute. So here we can do, yep, red italic. Let's run that again. Okay, so check this out. This one comes out. It says, okay, the address of the thing is 0x, the same as before. That hasn't changed because x hasn't moved. If we move this thing, then if we say let y equals x, then x will be dropped. We can no longer get to it, and y will have a different address, even though the value will be copied. So that's like copy and clone. So if we say let y equals x, then here what we do is we're dropping x. So this is no longer valid, x address 3. We're going to copy the value of x, which is 100, into this new thing called y, and this new thing called y will have a different address in memory. So we've moved it. That's the semantics of move. In terms of, I guess, memory layout, or yeah. So here when we run this thing, I think this is so much easier to work with, because we not only get the so what this says is that, okay, go get me the address of this pointer, and then get me the size of the thing that it's pointing to. So in this case, actually it's kind of like not really a pointer, because it's on the stack, and the thing that is pointing to is 1 byte. So this is a bit of a misnomer, but I mean, we could have done the same thing manually if we did this std mem size of value. So basically, if we wanted to also add additional information, we could say, let's say get size of x in bytes, and that would be like that, and then we could println it, and this is now, let's see, x size, let's do magenta, and this is still blue, so now we'll see the 1 byte. So that's roughly how this is just combining those two. It's getting the address and it's getting the size off. So let's go look at what this is. This is size of val, and there's a bunch of different macros for actually, sorry, functions for size off. So you can, yeah, it's a whole bunch of them. Size of, yeah, there's size of val, and I think size of val raw. So we're just using size of val here. And then, yeah, so there we go. So now we have a way to get the address of the thing on the stack, and we also have a way to get the size of the thing on the stack. So here, the way you read this is that, okay, x is a thing on the stack. It contains 100. The value 100 is stored in 1 byte of memory, because U8, it's 1 byte, but it can represent values from 0 to 255. So that's roughly how you read this. And this thing, this 0x blah blah 97 sorry, 79. This thing is 97. I said it right the first time. So the 0x97, this long string is just the address of memory for that particular variable x on the stack. So with this out of the way, so now we have this nice little macro we can use, so we don't have to keep having to write these complicated, I mean, it's not complicated, it's just tedious. So, okay. So now the first thing we'll do, now that we have that out of the way, let's delve into what exactly a box is. So, and what happens when you move a box. And like when you have a box, let's say you have a variable and you say box : new, and then if you assign that variable to a different variable, what happens? Does the box move? What moved actually? And what happens if you have two boxes and you don't want them to move, but you want them to basically switch the contents of their contents with each other in the heap, but you don't want them to move? So because of that whole indirection thing, we'll explore those two paths. And then at the very end, we'll look at pin. So these are three examples I wanted to show. Is that one is we're going to move a box. The second one is we're going to make two boxes. We're not going to move them, but we're going to swap their contents in memory, which is wacky. And then the third one is we're going to pin a box and then see what does that even mean? What happens when I pin a box? And by going through the first two exercises, we will have a pretty clear idea of what it means to pin a box when we get to it. Okay, so now that we have the basics covered, let's create our first example where we're going to explore what it means to move a box. So a box is a smart pointer that points to a location in memory and or heap memory, and then the thing that we put inside of the box, it can be whatever size because it's in the heap, and the box itself, because it's a pointer, we know its size as well. So so let's see, and then we're going to explore what happens when you actually move a box. So basically, if you have a variable, you create a new box and put in a variable, what happens when you assign that variable to a different variable? So let's call this, we're going to call this move a box. So here we're going to have a, let's make a new box. So let's say we're going to put a U8 in it, so it's a single byte. The value is 255. So let's get the address of the box. So basically, before we do all that, let's do this. And then what we want to do is we want to create a new, let's see, let's B2 like that, and now it's moved. And then basically, what does that mean? Like, what is the what changed between B1 and B? Like what happened to the memory addresses and so on? So let's do this. So the first thing we want to do is let's get the address of B1. So we can say B1 address, oops. And here we can use this this macro that we have, print pointer address size, because it'll display the it'll use the :p formatter to give us the pointer, the memory address, and it'll also print the size of what this is pointing to, so the pointee, so to speak. Actually, not pointee. In this case, it'll give us the size of this ampersand b_1. So let's see, and then we have so this is, wait, let's see, b_1. What does this do? Oh, okay, so it's like calling. Okay, I guess we'll see what the output of that is. I think it's gonna be oh yeah, I think this is gonna be the actual reference, not the value of the box. Like the pointer, this is the pointer, that's the box. So I think this will show the address of the pointer, not the box itself, if that makes sense. I guess we'll see it in a minute. And then we have Actually, before we do that, let's call this the reference address, and then let's get the address of b1 itself, which is not this symbol, it's actually b1 as ref. So this is actually going to get the this is the pointee, which is in the heap, and this is the pointer on the stack. There you go. So I guess we would call this pointer and pointee, but yeah. And then let's print it out to see what it looks like. Let's see. So we got b1 address and b1 ref address, and they're all blue, red, and red. So let's see. I don't think we want red. Let's do, actually, this is fine. So let's see what it looks like. So here we want to do move a box, and so b1 is, the value is 255. This is the pointee. The b1 as ref, that is this address, and it's 1 byte. So this is basically the address on the heap. So let's see. So this is b1 address. This is on the heap, and this is the pointer. So let's run that again. Yeah. So the b1 address on the heap is this 07 something something 10, and the size is 1 byte, which is important to notice. Let's not do red. Actually, let's do this. Magenta. Yeah, there we go. So here we have, actually, let's see, shortcut move. Yeah, that's it. Actually, let's just keep it running, because let's do this. Cargo watch, and I want to watch move a box. This way it'll keep basically showing the test output as I make changes here. So, okay, so we have the address on the heap, which is this number, hex something something 10, and then size is 1 byte. That's how you know it's not the pointer, it's the pointee. And the pointer is actually, let's do pointee, and this is pointer and stack. There we go. So so we have the b1 address, b1 underscore address, which is b1 as ref. That's giving us the pointee memory address and size, and then we're getting the pointer memory address and size. And notice the pointer memory address is bigger than the pointee. This is why I made the thing that's being boxed, I made that 1 byte so that we could see this difference. The pointer to the thing on the heap is 8 bytes. The thing that's on the heap is actually 1 byte. So this is pretty cool that we can see that. Another thing I wanted to show is that I like it when, like these strings, like if we can make them a different color so they stick out a little bit more. So we could do something like this. We could just do like green or something, and then here we can do basically take that out and do light green. It's kind of like just to make it a little bit more readable. So we have like b1 underscore b1 adder, which is how we got that is we use b1 as ref, and then actually let's just call it pointer. So this is the address of b1, and this is the address of the pointer to b1 on the stack. So, or I guess we could call this actually b1 pointer. There we go. So we got b1 address, which is a pointee on the heap, which is 1 byte, and then we have the pointer, which is actually bigger than the thing we're pointing to. So, and this is the, I guess we can say pointer. Oh no, it's too big. Just trying to make it all fit in one the width of the screen. So let's see, pointee heap, and this is pointer stack. You know what? Let's just do this stack. There you go. Okay, so now we have this nicely formatted thing, so we can understand what's going on. So B1 is on the heap. B1 I think should also be colorized. We can do green again. So there we go. B1 is 285. The B1 as ref. The thing that's the pointee, the thing the pointer is pointing to on the heap is this address, D10, and the size is 1 byte. This is the address on the heap. So this is this thing, the thing on the heap. So that's this address, let's say, is the D10, and the size of it is 1 byte. And then the thing on the stack, the pointer, the size is actually 8 bytes, and the address is something C8. So there you go. That's kind of visualizing what we see in that diagram, which is pretty awesome. I guess I should put a link to this here. Maybe I have it already. No. Okay. So so we have move box. Let's see. So now let's see what we can do. Actually, let's see. We call this actually, let's put the numbers on there as well, so we can actually see which lines we're printing, because that way it'll be easier to correlate the lines of output on the print line with what we see on in the code. I think I call this let's see, pointee and heap. So this one, okay, B1 is value on the heap. Okay, that's cool. And then let's see, we got the ampersand B1 as well, which is a pointer. So B1 is the variable that's on the stack, and we got a pointer to that. This is a way to get the address of that variable on the stack. Let's see, now we're moving it, and when we move it, we want to see what's going on with B2, like what's going on. So B1, if we try to access B1, we're gonna get an error. So if I run this, you see, it's saying, so that's great. We can't touch B1 because it's been moved. So then B1 gets dropped. So this reference is no more. But what happened to the value 255 in the heap, and like, did that get moved? So let's find out. So let's get the address of B2, and this is the same as before. This is like B2 that's on the heap, and we want the address of B2 as well, and I'm pretty sure that's going to be different than B1, and then we want to mix, and then let's print it, and then we're going to make some assertions. So let's see. Yeah, so we got B2 is 255. The value is the same. Look at this. The thing on the heap didn't actually move. So B1 had made a heap allocation of 1 byte, an address D10, which is still there, after the move of B1 to B2. B2, however, is in a different address. So B2 itself moved on the stack. I mean, the B1 got dropped, and then B2 is a new thing on the is a new variable on the stack. So here's the assertions. So we can say that assert not equal. Oh, right. So we can't do that because it's been moved. But what we can do, because we siphoned off the addresses, is we can say B1 and B2, their addresses are not the same. What got moved? Oh, so because we were, this is the, what happened now? Oh, no. moved by what? Actual error. Oh. So when I'm colorizing these strings, it consumes it. So I just put a clone. Okay. So assert. Oh no, that's not true. Wait. That is correct. It should be equal. No. So these are the things on the heap are the same. The thing that B1, the pointees are the same. So here we can say the heap memory allocation does not move. And what does move is that, yes, that's right. So here we can say, I think this is that same move thing, because oh yeah, the colorization. So just I can put a clone, and there's one more probably for that. Yep. Okay, clone. There we go. So there you go. These are the assertions that the heap allocation does not change, but the stack memory allocation has changed. So basic, yeah. So that's the kind of like the insight from these assertions is that the thing in the heap, it remains where it's at, but the thing on the stack is moved. So that is what the semantics of moving a box is. So not on the heap thing that's allocated on the heap remains where it's at, but the pointers aka boxes have moved. So boxes aka pointers have moved. The pointee has not. Pointee does not move. So I think we can refine the language a little bit more like this and like that. Okay, so that actually covers the semantics of what it means to have a box. A box is a smart pointer. The smart pointer points to something on the heap, and then we make another smart pointer. We assign that smart pointer to the first smart pointer, and so the pointers change, but the thing that they're pointing to does not. So that's pretty cool. Okay, and then of course if we drop B2, then it'll drop the heap allocation. So that's another consequence of it being a smart pointer. So we can say like when B2 is dropped, the heap allocation is also dropped. Is deallocated, exactly. So that's why it's a smart pointer. This is yeah, because this is why box is a smart pointer, because it's not just a regular pointer. It is a pointer with other like capabilities or powers. So now what I want to do is another example where we have two boxes, and I don't want to change the smart pointers, the pointers, but I want to swap the pointees. Just to get an understanding of the distinctions between like pointers and pointees. So this one is actually swap box contents. So let's do this, and okay, so this will run all the tests. So I don't want to run all the tests, I just want to run the swap one. So I'll just say output swap. There we go. Okay, so here what we want to do is make a box with, let's say, 100, and let's make another box. So this is allocate. This is basically a pointer, smart pointer that's pointing to a heap allocation of a byte, which has the value 100 in it. This is the same thing, but just a different allocation on the heap. This one has 200 in it. So now what we want to do is we want to swap them. So the way we do the swap is we do swap like that, and that swaps them. So basically we can see that they've been swapped. We can say assert eq, we dereference b1, whereas it used to be 100, we expect it to be 200, and now we expect b2 to be 100. So basically it's flipped. And as you can see that the assertions are passing. So that's great, but I would like to see like what that means with memory addresses. So this is like the pointers are stable in this case, but what they're pointing to got switched out in memory. So it's the upside down, so to speak, of not upside down. In the previous test, we were moving the pointers, and here we're moving the pointees, while keeping the pointers the same. So this is the kind of crux of it. So let's look at the addresses and stuff. So what we also want to verify that the B1, like the pointer B1 and the pointer B2 have not changed. So let's grab the addresses for them. So let's do OG B1 address equals that. And let's do OG B2 address. Okay, so now we have the B1, B2 address. Now when I swap them, we can say, let's see. Well, is it after swap or swapped? Let's just say, yeah, new B1 address, sure, and new B2 address. So now the assertion is that they're both going to be the same, and that this one, basically that the pointers haven't moved, but the contents have been flipped. So, and here we can make an assertion that, you know, before the swap, we can say assert that B1 is 100 and B2 is 200, which is correct. But then after the swap, it's flipped. So this is an example. And if we wanted to print out the address, we could just, because the addresses are stable, we can now say print, we can say something like, this is that right? B1, what is this? Pointer, let's see what it's doing. It's got new B1 address. And yeah, I think that's right. I mean, OG B1 address, new B1, they're the same. So yeah, I guess it doesn't matter. Yeah, so basically it's saying that B1 has a value of 200, not 100. And the address of B1 is this number, and sorry, the thing that B1 points to is this address. And so I guess what we would want to do is print it before and after. So what we can do is do this println, do the same for B2, and instead let's do it before and after. So let's do same thing before and the same thing after, before the swap. So we can do println, and we can do println. Okay, so before we're using OG B1 address, OG B2 address, that's right. So ampersand B1, ampersand B2. And afterwards, ampersand B1, ampersand B2 is the same, only now we're doing new B1 address and new B2 address, not OG. And let's see what the results are. So for B1, we have something ending in 10. And look at that, B2 now points to that. So it did get swapped. So if we were to clear code this, where we're saying that, let's say all the let's say B1, we want it to be, let's say, we're going to make this red, and then let's see, and then this, wait, this is, so B1 is red, and then because B1 has moved to B2, now this should be red, I think. Oops, nope. I mean, this should be red. Okay, that's right. So these are the same. That means that the thing that is being pointed, the pointee is the same for, like, even though, like, what B1 was, the pointee for B1 is not the pointee for B2, because that's what it means. We have swapped out the pointees, but the pointers are the same. So that's how come their places have flipped. So if we put a little line break here, we can say swap to B1 D2. This one we can say green or whatever. Let's see, cyan, underlined. And so when you do print line like this, you have to do like this. There we go. Okay, so we swap B1 and B2 here, and then so the pointee, the value of 100 is actually in the same memory location as it was. The 200 is in the same memory location as it was. However, and these pointers are the same. So basically B1 is still at 80, and B2 is still at 88. So yeah, that's actually stable. So actually, if you wanted to color code that, we could do like, because B2 is going to be stable, so this can be cyan or something, and then so we know that B2 will also be stable, so this one we can do cyan. There we go. So if you look at the output, you can maybe kind of see based on the colors like what is happening. So the 100 swapped places with 200, but the pointers were still pointing to, like the P1 pointer is still pointing to the same location as it was before. So like the references haven't moved on the stack, but what has moved on is the heap. So they just got swapped. So hopefully that makes sense. That means the B1 it was here, B2 is here. They haven't moved, but what B1 was pointing to, that switched places with what B2 was pointing to. So, and so their memory addresses literally got swapped. So that's pointer indirection. So there you go. It's hopefully this adding some color to it makes it a little bit easier to parse. Okay, so now that's done. Let's do another one, and this one is going to be pinning. Like what happens when we pin? Like what, you know, why are we pinning, and what happens when we use pin in conjunction with box. So here we have box and pin dynamic duo. So this one we can do dynamic. Okay. So here the box provides heap allocation and ownership. So this is necessary when the size of the data is unknown at compile time, it's like with trade pointers. The pin provides stability by preventing whatever's pinned from moving in memory. And this is crucial for async code when there's futures involved. and for things like cancellation safety, or using things like, not cancellation safety, but when you use Tokyo select macro, this is important. You have to typically pin the thing that you're selecting on, and we're going to see why. You have to pin the thing. Like boxing isn't enough. We've seen what happens with boxing, where we can box something and it puts it on the heap and takes it off the stack, which is nice. But when we pin the variable, we won't be able to change its address anymore. So let's demonstrate. So to do this, let's make a box. So we'll say with 100, and let's get its address. So we get this is the address of the pointee, not the pointer. But this is the pointee, so that's what this is. And so then we have, we're going to pin it. So we can say let pinned b1, and there's many different ways of pinning it. We can use a macro called pin. It comes out of the standard library. We can use a function called pin on box, which is actually what you would use if you wanted to return it from a function. But because we're using it sort of inline, we're just going to ask the b1 to pin itself. So we're going to say into pin, something like that. And yes, that is correct. So that's what it ends up looking like. So basically we're saying, we're asking b1 to pin itself. And so if you look at the type that comes back, the type of b1 is a boxed u8, and the type of this thing is pinned boxed u8. So now we're going to get a sense of what pinned means. Like why did we even pin it? So we can actually get the address of the pinned variable. So we have another macro called print pin address size, and it just takes the symbol, the pin, and it will basically get the address of the thing that's the pinned reference, or the pinned variable, and it'll also get the size of what is pinned. And what this syntax is, it's dereferencing and getting a pointer to it. Basically, it's looking inside the pin, and it's giving the size of the box. So that's what you kind of like read it that way. This one, the declarative macro. So star dereferences it, and then ampersand gets a reference or a pointer to that thing that got dereferenced, which is you unpin, basically look inside the pin and you see what the pin is pointing to, and it's getting the box u8. That's what this is. Okay, so now what assertions, I wonder, can we make now that we've pinned it? So also, like, what does it mean that we pinned it? So let's do this. Let's say let's make another variable, and this variable I am going to, because it's kind of like we did this in the start. We said we made a box, and then b1, and then we said b2 is b1, and then we saw it moved. So is this going to move? Because if it does, then what was the point of pinning? And the answer is no, it won't move. That's why I'm using this as an example. This is the difference between pinning and not pinning. So we said b2 is pb1. So, you know, okay, this is going to be dropped, and it's going to move, right? Well, no. So this is where things get a little bit different. So let's do b2 address. So we can say, nope, it's not pointer. This is pin, and it is simply b2. Notice the type of b2. It's actually pb2, because the type is pin, even though I said b2. That's pretty cool. So right away we know something is up. So now let's see what assertions we can make. So is the is the address of let's see, so we can say b1, this one, the thing that the pointee, right, is the same as the thing at the end, which is great. That means the pointee has not moved. What about the pointer? Our assertion is the pointer has not moved. So if we say, okay, let's get the, actually we've already done this. It's called, let's see, PB1 address. So let's do B1 address. Sorry, we need not PB1 address, do B1 address. Then we do, where's PB1 address? Oh, PB1 address. There we go. All right. So far so good. That means that the B1 address, which is the pointee for B1, which is this 100, is the same as after we pinned it, which is unsurprising, right? So the more interesting thing is, what is this B2 address? So check this out. So now if we do assert equal B2 address, oh sorry, and B1 address, oops, and PB1 address, which is the same as B1 address, they're all the same, which is why an easy way to read this is this thing. So we're basically saying that, okay, B1 address, which is this is the pointee, then we have the, oops, pointee, then we have here, this is the pinned, whatever, the thing that we pinned. And then this one is the, we looks like we moved it, but we can say that pin does not move. That's what that means. So basically, even though we made, and by the way, we cannot access PB1 anymore. So if we try to do something like this, notice that that errors out, as it should, because PB1 has moved and dropped. This is no more, but because it was pinned, it doesn't matter, because it didn't get moved. The compiler won't move it. So that's what pinning means. So there you go. This is what pinning is that even after doing all this, you know, normally last time we did this with, where is it? I think we did, was it move a box? Yeah, when we did B2 equals B underscore, you know, B2 equals B1, we saw that we couldn't access B1 anymore, but the address of B2 had changed. Now after pinning it, we're seeing that the address of B2 has not changed. And I mean, I kind of wrote it as B2 on purpose rather than P underscore B2, but that's essentially what's happening, is that even, and so basically I could have just pinned this to begin with, called this, you know, pin B1 or something, and then you know, even if I assign it to a different variable, it's not going to move. So there you go. Hopefully this makes a bunch of sense. And like before, we could actually print out some of these, what the actual values are. But I mean, it doesn't particularly matter to us what the exact numbers are, because they'll change every time the program runs. But regardless of what the specific numbers are, we know that it's not being moved. So that's the semantics of boxing and pinning. It's quite a bit different than just a regular move semantics. So with that, we have like the 3 tests to kind of go over, like boxing, moving boxes, having 2 boxes, swapping the contents of the boxes, but keeping the boxes, aka the pointers, the smart pointers, the same. And then finally, pinning a smart pointer and seeing that once it's pinned, even if you assign it to a different variable, it doesn't matter. The old variable will be dropped, but the new variable will have the same address as the old one, and that's what pinning is. And that's why it works with async code, because the addresses are stable, in between iterations of the async polling loops. So yeah, that's been a deep dive of pinning and boxing. If you like the style of this video, please give me a thumbs up and subscribe to the channel. You'll be notified when new videos are available. And if you haven't already, please subscribe to Developer Life. This is the article side of the video channel. The YouTube channel. So if you subscribe, when I create new videos and blog posts or articles that go along with them, you'll get an email, and these aren't that frequent. And then, you can also check out this code. I'll post a link to this in the description. There's usually a repo that goes along this video. You can clone it and play around with it, and get more familiar with these different pinning, moving, and getting the addresses of things. And I'm working on another video right now on lifetimes, which should be fun as well. Kind of getting a bunch of, and I might actually do one on like copy and clone at some point, maybe even sized. So yeah, and also we have a Discord if you have any questions and comments. I don't have comments on YouTube or any other socials except for Discord. So please, I'll post a link to the Discord server in the description of the video. If you have any comments, feedback, thoughts, please let me know on the Discord server. Thank you so much for watching, and I will see you in the next one.